Hello and welcome to this third video in this series where we are learning about agentic workflows. In the last two videos, we learned about what are tools, how to bind tools, how to create tools, stuff like that, how to empower LLMs with tools. Now, today we are going to dive into the real stuff. Today's video is going to be a kind of a practical introduction into agentic workflows, and we are going to learn about LangGraph. So this particular video is going to be structured in this manner. First of all, we are going to see why do we use agentic workflows, why even study about it. Second, why LangGraph, what is LangGraph, why should we use it, and then we are going to dive into LangGraph basics, and then we are going to create some basic flows and graphs inside LangGraph. Okay, so all right, let's first dive into why LangGraph, right? So this is how a usual LLM chain looks like when we are talking about. All right, let me zoom into it again. Yeah, this one. So up till now, we know about different kinds of LLM chains that we can create using LangChain, using Llama Index, stuff like that. And a general LLM chain looks like this. Imagine any generative AI application, a RAG application, a chatbot, anything. It usually has this kind of a workflow. It's a simple chain where some basic functions are being processed in a particular sequence, right? So a user writes some kind of a query, then that query gets enriched in some way. This can be enriched through RAG, this can be enriched through tools or anything else that you might come up with, but it's basically enriching the query, adding context to it, providing more information to it, and then the entire dump of that enriched query with the context and whatever you can basically feed into it. We dump that entire thing to the LLM, and we trust in the almighty LLM to generate the final response. If the final response is good, we say that okay, the app is working fine. If it's not good, we need to basically figure out how can we change these particular functions, So this was a usual LLM chain, but guess what? Here, if you look carefully, we are basically using LLM just as a very good or an ultimate level text processing machine. We are providing it a lot of jumbled up text with some relation in it, and the LLM is trying to process all of that to generate a good final response, a structured response for the user to swallow or digest, So the problem with this LLM chain is, number one, in this chain we are not really harnessing the power of LLMs. LLMs are much more than general text processors. I mean, that's what they are basically, but we can get a lot more value than this. Second, we are trying to create a dynamic workflow for our application. What I mean by a dynamic workflow is that, say that if the final response generated by the LLM is not good enough, I want to generate a better response dynamically without requiring any further changes to this chain. So for example, I can think of a workflow where user enters a query, the query gets enriched, gets fed into the LLM generates a response, and then the LLM again judges that particular response in some way whether it's good or bad, whether it should be displayed to the user or it requires some more modifications, does the query requires more enrichment, stuff like that, where we are trying to introduce some kind of dynamic stuff into our workflow. In that case, we will rely on agentic workflows. So agentic workflow is nothing but we are trying to empower our LLM and provide it some kind of decision making power so that we can have a dynamic workflow and we can have a system that can do much more than just producing text and using LLM as a text processor. So this is one resource that I'm working on currently, but we can rely on this to just learn about a few things. So you can think of an agentic workflow as an attempt to provide more power, decision making power, and more control to our LLM. Now, this is a particular diagram that I've taken from LangChain. It talks about two extremes. In the first extreme, it's talking about an agentic workflow that provides very less amount of power or control to the LLM. So you can look at this workflow. It starts, goes to step 1, then feeds that step to the LLM. Then the LLM can actually make a decision whether I should proceed with step 2 or I should proceed with step 3. So this is called a routing mechanism. We know about it. I think we did it in the last video. If you don't know about it, this is it, where the LLM can basically decide its path. Now, this is one extreme. In the next extreme, we have an LLM that can make decisions on which steps to call, in what order. I mean, it has got complete power over the workflow to the extent that no workflow has been described here. The LLM decides everything on its own. So, why do we need to know about this? Because of this particular graph. As the Gen AI apps or the agentic workflows go on getting more developed and advanced, we need to understand that the more decision making power you provide to the LLM, to the model, the more you lose reliability and the more the response becomes inconsistent. Why? So you can look at this graph here. It shows the router on one extreme and the application reliability is super high, but the agent's level of control is low. On the other hand, the autonomous agent has very high level of agent control. The agent basically controls everything, but it has not got a lot of application reliability. Why? Because you know that LLM is a probabilistic kind of a model and it can be pretty inconsistent in generating responses. All right. Now, where does LangGraph come into this? What LangGraph is trying to do is it is trying to bridge the gap between these two extremes. It is based on this idea to enable us to create agentic workflows that provide some kind of control to the agent, but at the same time are highly reliable and production ready. Okay. So, what is LangGraph? LangGraph is basically a library to build stateful multi-actor applications using LLMs designed to build multi-agent workflows. Okay, I've written this. I've copied this particular definition, but this is quite complex to understand. So, as I've written here, instead of deep diving, let's just start off with working with LangGraph and we can understand why it's so cool and how easy it is actually to create agentic workflows with LangGraph. So first of all, I'd like to talk about some key concepts of LangGraph. Okay. So Alright, let me just go here and start off with it. So we are going to talk about key concepts of LangGraph. LangGraph comes from the same company as LangChain, but one really cool thing about LangGraph is that while using LangGraph, you are not compelled to use LangChain, but using LangChain basically makes life easier. So the first thing that we're going to talk about is something called as state, right? Now you can think of LangGraph as a graph, or a flow rather, that takes an input, a state, and updates the state as its output. So what I'm talking about is, there is an initial state, which is fed to the workflow, or we call it graph in LangGraph, a particular graph. I'm going to show you some graphs in just a minute, okay? Then it'll get clearer. And then as an output, we basically receive the final state. So you can see from this particular flow that a LangGraph graph is basically a state machine that converts the initial state to the final state. But what is the state, right? You can consider the state to be simply a dictionary. A dictionary where the structure of this dictionary will be defined by us, and it will depend on the nature of the graph that we are planning to create. One simple state example can be just graph state and string. Okay. So this means that as an initial state, it will take a dictionary, and the graph will modify this dictionary throughout its flow elements, its entities. It will do a lot of stuff, but all that stuff will basically result in a final state that will be a modified version of the initial state dictionary. Here there will be something called as, say, string 1. So it has changed, right? So you can consider, that's why they say that you can consider a LangGraph graph to be a state machine. Why? Because it takes in input a state and it converts it, it modifies it into a different kind of a state, and that's what we digest as the output. Cool. So the rest of the things we are going to learn on the fly while working with our first graph, this one. Okay. You can see the structure. There is an initial state, there is a final state, and there are a few things in between. I'm gonna let you know what are these. So the first graph, I'll be showing you how to do it in the Jupyter notebook, but first let's understand what I'm trying to do here. The first graph which I have created is basically, I do not have any LLM. You might be seeing that there is no LLM in the process. I've tried to keep it very simple because first I need to teach you how to use LangGraph and how does a LangGraph graph workflow looks like. So here we're taking this particular dictionary as the initial state. It has got the key as graph state, and there is a string in here, fiddler here. This is the string that I'm taking in it as the input or the initial state. Now it goes to the first node. Now what is a node? Simply speaking, you can say node is anything, or I should rather write is an entity in a graph that changes the state. Looks very huge. I should rather decrease its size. Okay. So node is an entity in a graph that changes the state. It means that if you input a particular state in a node, you are expected to receive an updated state as the output. I should use the word updates instead of that. So node is an entity in a graph that updates a state, and a node is, all right, come on, okay, yeah, and is defined as a function. So you can simply understand it like a node is basically a function that takes in a dictionary or the state, modifies it in some way, and then provides an updated version of that state. Okay. And then there is a second thing. So let's mark it as red. This is the first concept of node. And then we have another concept called as edge. All these connections that you see here, connecting one entity to the other, is basically an edge. So edge is an entity of a graph that connects two entities. Pretty intuitive. This is pretty intuitive because whenever we are creating a graph, we need connections, right? Whenever we are working on a flowchart, we need these arrows or these connections to actually showcase what's happening or how are these particular entities connected to each other, right? So let's mark it on blue. And this is the second concept. And the third concept is a conditional edge. What is a conditional edge in LangGraph? A conditional edge, this is the conditional edge over here in this particular flow graph. A conditional edge is something that branches into two or more nodes, or two or more paths rather. What happens is, this particular condition edge is taken in input the state which has been provided as an output from node 1, and then this conditional edge decides whether to push this particular output towards node 2 or towards node 3. Now, how does this make a decision? First of all, I'd write a simple definition of conditional edge. Conditional edge is an entity that makes a decision about the pathing that would be followed, or you can call it pathing, or you can call what next step needs to be taken, which node should be accessed after this decision mood conditional edge. So it's basically the decision flow kind of a manager that controls the flow of a particular graph. So marking it in green. Now, how does this work? A conditional edge can be defined, can be thought of, or can be defined as an if-else statement, where we can define an if-else condition. If, say, it's raining, go to node 2. If it's not raining, go to node 3. Something like that, okay? So this particular entity is the one that makes decision about the flow of the graph. Node is the entity that changes the state or updates the state, and edges are the entities that basically connects stuff, okay? So the graph which you see here, we are going to try to create this graph, and let's see the magic happen on ground in a Jupyter notebook. All right. So you might be seeing that I'm not typing out the code today because I think this video is going to be very long if I type out all the code. But comment if you want me to upload this notebook, I'll upload it. or I'll just upload it later. I'm a bit lazy about that. So let's start with it. Okay, you can pause the video, do stuff with it, all that shit, right? So anyways, cool, let's start with it. But before I start with it, I just remembered that I need to tell you something else, a very important thing, so that you don't get confused and you are right on track. So this is how we develop graphs in LangGraph. So this is the LangGraph development flow that we'll be following. Every single graph that you develop on LangGraph is going to use this particular flow. Very simple, very sweet. First of all, you know that LangGraph is a state machine, right? It updates a state, takes an initial state as an input, and provides a final state. So first thing that we need to do is define a state. And reducer. What is the reducer? I'll just tell you in a minute. So we need to define the state. How is the state defined? We can use some predefined states from LangChain, or we can define our own state by creating a class. After that, after defining the state and the reducer, we will go towards defining the node functions, the tools, the conditional edge functions, basically all the utility that we will be using in our graph. We will be defining the node functions, the tools, if we require any kind of tools. I'll be showing you how to create a tool-based flow in this video later, and we need to define any conditional edge functions, the if-else things that I was telling you about. We also have some pre-built or already existing conditional edges in LangChain. I'll show you how to use that as well. After that, we create the graph builder object. This graph builder object is nothing but it is an interface through which we can create our graph, add entities to our graph in a particular order. We can add edges, nodes, and conditional edges to our graph and give it a shape. You see, we create the graph builder object. After that, we add nodes, edges, and conditional edges to it, whatever we require. And then we compile that graph object and execute it to get the results. Cool. Sweet. Now let's move to the Jupyter Notebook. So first thing, I have to define the state. Now the graph that I am willing to create here is this particular simple graph that I've showed you here. So first of all, I'm defining the state. I'm using the typed dict class from typing library. You can read about this. And I'm defining my state. So you can see this state looks like very simple. It's going to be a dictionary that has only one key, graph state, and this will take, and every value will be a string. The value will be a string for this particular key. So it will accept stuff like graph, state, and anything, but the value should be a string. So blah blah, anything. Okay. All right, now let's execute it. Now our state has been defined, it has been created, right? Now let's look at what the next step was. It was defining node functions, tools, and all these utility things. So as I told you earlier, all the nodes are defined as functions that take in input a particular state and then update it and return the updated state as an output. So first of all, we need to define each particular node as a function. So coming back to my flow, we have 3 nodes here, so we need to define 3 functions. So the node 1, let's see what the node 1 is doing. It takes in input as the state, and then I'm printing node 1 here for clarity while executing. And then we are basically creating a variable updated state that will be returned. The updated state is graph state, where I'm adding this particular string to the initial state, whatever the initial state is. Now I know that that initially it won't be null or it won't have any string, because I will control the flow of this particular graph. So we'll see that happen. We'll see that while executing. So what I'm particularly doing is I'm taking in a state as an input and returning an updated state where I've made some changes to this particular dictionary, and then I return this particular state. In node 2, I do the same. I take in a state as input, and this time I'm adding this string to that state. Very happy. Good. And in node 3, similarly, I'm taking in a state as an input and adding the string very sad to it. And in this way, I'm modifying or updating the state and returning it as an output. All right. And I also need to define the conditional edge function that I'll be using. Similar to nodes, if we are creating custom conditional edges, why am I saying custom? Because LangChain provides us some pre-built conditional edges as well. We'll be looking at them after some minutes. We need to define it as a function as well, as an if-else statement, as you can see here. So the function which I'm defining here for the conditional edges, defining the conditional edge function, define decide mode. It also takes in a state as a function. Why does it need to take a state as an input? Because depending on the output state of node 1, it will decide what decision it should make, right? So literal node 2, node 3, why are they depicted as strings and not as functions here? I'll tell you that in a minute. So what it will do is, it will take the user input. What is the user input? The user input will be the state, graph state. It will provide you the current status or the current string inside this particular state. And what I'm doing here is, I'm creating a 50% probability of choosing a path. Basically, I'm just trying to tell you how this conditional edge works. So what I'm simply doing is, if random is less than 0.5, return node 2. If else, return node 3. So what it will do is, 50% of the times it will switch to this particular flow, and 50% of the times it will switch to this particular flow. And let's look at our development flow again. We have defined the node functions. There are no tools in this particular graph, so we have defined the conditional edge functions. Now we need to create the graph builder object. Creating the graph builder object is pretty easy. You just import state graph start end from this library, and this particular library we have imported because this helps us visualize the particular graph that we have created. Okay. Then we initiate the graph builder object. Builder equals state graph state. The graph builder object requires the state which will be flowing through our graph as an input. Alright, now we have created the graph builder object. Now we need to add nodes, edges and conditional edges to it. Okay. So adding a node to a particular graph is very easy. Just take the builder object dot add node. Now one thing, the syntax for adding a node is, I'll just write it here, is builder dot add node, node name comma node function. This is the syntax that we are following. Okay, I'll just comment it out. Okay, good. I've commented this, and this node name will be a string, will need to be a string. So we know that in Python we do not refer to functions as strings, we refer them to as function objects. But when we create a graph, we refer to the nodes as a string which contains a node name. So here I have added the node 1 function, and the name of that node is node 1 simply. That is the reason why I have used strings over here and why I have returned these strings, because this tells the conditional edge that if the random number is below is less than 0.5, return a node 2 string. Node 2 string refers to the node 2. We add all these 3 nodes in this particular syntax to the graph, and then we start adding the edges. Now, the syntax for adding edge to a particular graph is builder object dot add edge start entity end entity. Whenever we are adding an edge, we need to specify where it's starting from and where it's ending to. Now, you see the first graph, the first edge starts from initial state and goes to node 1. So we do not refer to the initial state as initial state in a graph. In fact, for a graph, there is a start point and an end point. So we can also call it the start here. Start. Let me just go place it in black and place it somewhere here. And I would rather select all of this and place it a bit. Okay. So this is the start, and similarly this is the end. Okay, so the first edge goes from start to node 1. Let's see it here. So builder.add edge start entity is start and end entity is node 1. Now what is this start? This start is basically a start is a particular thing which we can import from LangGraph library that depicts that the graph basically starts here. And then after that, the second edge is going to be a conditional edge which starts at node 1 and ends on node 2 and node 3 depending on what happens in this particular conditional edge. So add conditional edge. The syntax for the conditional edge is similar, but the syntax for a conditional edge goes like this. Builder dot add conditional edges. Notice the extra s over here, and then start entity, and then decision, or I would say conditional function. So the conditional function here has been defined as decide mood because it decides my mood based on the basis of probability, because that's how it is, right? So the decision making or the conditional function is decide mood. So I've added it here, and it starts with node 1. Now I do not need to define these edges. Why? Because those have already been attached to this particular function. So if the random number is less than 0.5, it returns node 2. So we do not need an edge. It already this particular conditional edge is already connected to these 3 nodes. Starts with this node, might end on any of these nodes. So we do not need more edges for these. Pretty intuitive, right? And then we need to add these edges. So both of these edges need to connect to the end or the final state, because we might receive the final state from node 2 or node 3 depending on the conditional edge. So builder add edge node 2 to end and node 3 to end. Coming back to the development flow, We have added the nodes, edges and conditional edges to the graph. Now we need to compile and execute them. Compiling the graph is pretty easy. Graph, we create a graph object by compiling the builder.compile. And if you have any errors that you might have committed while creating this graph, while defining the graph, you will get an error on this line while compiling it. Okay, now I'm executing it. I'm getting this visualization because I used this particular line. It is using the graph.getGraph method. Graph has been created after compiling it to basically visualize this entire thing. It's pretty helpful whenever we want to visualize the graph that we have created before executing it. Pardon, I'm having water. Okay, cool. I don't know why did I get thirsty. Cool. So our flow starts with start, goes to node 1. The dotted lines signify that there is a conditional edge over here. It might go to node 2, it might go to node 3 depending on the conditional edge, and then it goes to end. Cool. Now we want to execute this particular graph and see it in motion. Now a very cool thing is that every graph object is a runnable. What is a runnable? A runnable is a protocol which is created in LangChain. It is a part of the LangChain expression language, LECL. If you want me to tell you about or teach more about LECL or the runnables and all these things related to LangChain basics, you can just put it in the comment and I will see to that. Cool. Now executing the graph is as simple as graph.invoke, and we need to provide the initial state as an input. So my initial state is graph state fiddler here. Matches this, right? Graph state fiddler here. This is the initial state. Cool. Now I want to execute this. Okay, this has been executed now. Node 1 ran successfully and updated the state from fiddler here to fiddler here I am. Then it went to node 2 because of the 50% probability thing, and the updated state is this particular updated state has been generated by node 2. Fiddler here, I'm very happy. Cool, I'm very happy. That's great. So you see what happened basically is that you provided an initial state and this state got modified as it passed to the different nodes, and finally you received this particular state. Now you must be understanding what a state is. A state is like what flows through a LangGraph graph, right? Cool, very cool. let's run it again till I get sad. Okay, I got sad pretty quickly, eh? Fiddler here, I'm very sad because this time the conditional edge decided to run node 3. Cool. Now you might be thinking, but brother, where is the LLM in this? I know, be patient. This particular exercise was to help you understand how LangGraph works, how nodes work, how conditional edges work, how edges work, and why is it called a state machine. Now we can get going with the real stuff of men. Now we'll try to design this particular flow. Boom. We will try to take an input as initial state as always. We will take this input to a particular node containing an LLM. The output of this LLM will be fed to a tools condition or a conditional edge. This conditional edge will decide whether to basically push this towards a tool or push this towards the final or the end state or the end of the flow directly. Now, to explain you this a little bit, I will go to Jupyter Notebook again and we will get on going with the code for this. But one thing, okay? You remember I told you that I will tell you about reducers while going through this flow. Now is the time. Okay. Why do we need reducers? What are reducers? Okay. Now, okay, we need to shift this over here. Okay, cool. Before this, I want to talk to you about reducers. You see, you can understand by this particular example of a graph that we made that a graph needs to take in an input as a state and then go on updating it. But usually what happens is that every node returns a particular dictionary which does not update the existing dictionary necessarily. What I'm saying is that while defining each of these nodes, I made sure that I'm updating the existing dictionary, the existing state. Don't be afraid, I'll be using the word dictionaries and state interchangeably because they are the same, okay, no matter what you say. So I took an input as a state and I updated it by adding this string to it, okay? But this was because of the nature of this particular state. What if I'm working with a state like the one I'm creating right now, which is the most popular state? You'll be using this a lot. Okay, first let's define a state, or let's define a messages state. Okay, so I'll be taking an input from typing, import annotated, from typing extensions, import typed dict. Cool. Now I'll be defining the state. So class, I'm calling it as just state, okay, state, and cool, yes sir, I want it to be typed dict. Why do we use this particular typed dict thing? Because it makes it easier to define a state which is a dictionary, okay? It makes life easier. You can study more about it. And my dictionary or my state's structure is going to look like messages, and it will be a dictionary with a key called messages, and the value inside this key will be a string. I want it to be a string so that every output I get from the subsequent nodes I want to append into this particular list. So I want it to be a list, so I'll go ahead and I'll write list. Okay, now what is the challenge with this? Say that the first node takes in input this particular string's first element, processes it, and then returns an output list. But we do not want an output list. We want every single node to update the existing list, right? So there can be two ways of it. One way is we can simply make sure that we create a logic so that whenever we are executing any node, it appends the output of that node into this list so that the state gets updated and does not get replaced. We don't want the state to get replaced. We want the state to get updated. Updating this particular state would be just appending new things into this list because it has only got one key, right? Messages. So it would look like this. This particular state would look something like this, and a list. So say that the initial state is hi, this. What I want to do is I want to, what the flush, all right. I want, so this is the initial state, say initial state. What I want to do is after node 1, the first node, I want it to do, what I want the node to do is provide the response, generate an output, and append it to this particular list. And then again the list keeps on getting appended and the state keeps on getting updated so that we receive the final state at the end. But for this, as I said, we will have to design a mechanism in the function itself, which is underlying in the node, so that we append and not replace that state. For this, the mechanism which we are going to use is called a reducer. A reducer, in simple terms, is basically a mechanism using which we ensure that every node updates the state efficiently and consistently. Okay, so I'll show you how we can use a very popular reducer which we are going to use again and again and again. It's called is it from LangGraph, LangChain? I don't remember. From LangGraph or from LangChain core, import add messages. It's just this, or maybe I'm just a second, okay? Just a second. Messages saved, alright. I don't really remember which library was it. Just let me see again. Alright. Cool, it might be this. It might be LangChain core. Let me run this, let me check. Okay, it's not from LangChain core. Is it from LangGraph? Let me just search it. Let's see. LangGraph, just see, add messages, LangGraph. Okay, alright, add messages, brother. Okay, maybe we'll get something here. Alright, LangGraph.graph.message. Cool. Yes, LangGraph.graph.message, import add messages. It works. Okay, so add messages is a reducer. What it does, this basically ensures that every single node updates the state, or in this case updates this particular list, and does not replace it or do something which is not intended. Okay, add messages is very simple. It is just a function which takes in input to particular lists and appends the second list into the first one. So you can see it in action in this way, so that we create two lists. List 1 equals A, B, and list 2 is cd. So if I go for add messages, list 1 comma list 2, let's see what it gives. It basically appended all of this in a particular format. You see this human message object over here? This is the stuff that LLM eats. You know, every LLM takes an input as human message, AI message, system message, all those things. You can learn about those. Okay, so basically what add messages does is it appended CD into AB in the particular format. It basically made sure that everything works. Okay, now how do we add this reducer to our state? Very simple, using the annotated class. Just go here and go for annotated list comma add messages. Just doing this, what is the issue with this now? It works, right? Okay, fudge. Cool. Cannot be instantiated, type predict, annotated, all right. I think it's in this way. I think it's square bracket or something. Yeah, cool. Now it works. So just writing this line makes sure that whenever this particular state is taken in as input, this add messages reducer ensures that the list gets appended and nothing goes wrong. Everything is in the right format and stuff. Okay, cool. Now this particular class which I created, the state class, which has the messages as a key and the value is in the form of a list, is a very famous class and it gets used again and again in LangGraph. So what LangGraph has done, they have included this particular thing as a class in their library, so we can use it straight up. You can see. Cool. Okay, now that we know about reducers, we are safely stepping into our first graph, which is this one, which is going to be a graph with a tool enabled LLM. Okay, so first of all, we define the state as usual. Class state, message state. We are inheriting from message state, which is a class created by LangGraph people. And so here we define the state, and then we have to create a tool because we want our LLM to be binded with the tool in this case, and enable our LLM to make tool calls. Okay, so we define a tool. You know how to create a tool, define a tool. You can check out the earlier videos in this playlist where we learn how to create custom tools and how to bind them to LLMs. So we define the tool function. First of all, we import this particular class from langchain.tools, and then we create the tool function, which is a multiplying function, takes in input two particular numbers, int, integer type hinted. The docstring is multiply two numbers a and b, and then return the multiplied thing. And then here we just assign it as a tool using the structured tool class, and then we create an LLM runnable. Just imported OpenAI. We are using ChatGPT 3.5 turbo model, and then we bind it. Create the tool list, just creating the tools list, and then binding it to the LLM. So we create a new runnable LLM with tools, LLM.bind tools, you know this stuff. All right, now we have binded the tool to the LLM. Cool. Now we go towards creating a node. Here, Here you see we have got this one node, LLM, takes an input and provides an output. So we define this particular node, define tool calling LLM, we take an input state, message state, and return messages. You see, we are simply returning a list over here. We are not explicitly performing any updation or any appending operation on the list. That thing will be carried out or will be taken care of by the add messages reducer. Okay, so we just take an input and LLM with tools invoke, and yeah, done. This particular node is done. Now we start with creating the builder. Now you might be saying, brother, you did not create these nodes, I mean tool or anything else, or the conditional edge, you did not even define the function for this. Why? Because here we are going to use some built-in conditional edge and built-in nodes. So I'm going to go here. All right. No, we are not going to use any pre-built one here. That's my bad. That's for the next graph that we are going to see. It's going to be a simple one, so it will just take tools condition. My bad actually. Yeah, cool, okay. Yeah, so what this does is we are adding a node. We added this particular node, and then we add an edge, start to tool calling LLM, and then we add an edge, tool calling LLM to end. So tool calling LLM to end. You might not be seeing all these here. I'm going to add these later actually, but yeah, we're going to see it. So this is how this worked, and yeah, we are going to execute this now. This and then this. Looks pretty basic. Start and then tool calling LLM and then end, right? Now let's execute it. Our initial state is basically the user query which you want to feed to the LLM. We'll start off with something that requires calling the multiplication tool, multiply 2 and 3, and then the response is going to be graph.invoke. Alright, let's see what the response is. Response, yeah. So the first one is the human message, multiply 2 and 3, and what we got as AI message, we did not get any content, it's just a tool call. You can see here it provided the arguments, the values in the particular argument schema required by the tool. You can learn about tool calling from the previous videos. So as expected, this simple graph took in this particular input and then converted it into a tool call. Now what we want to do is, but you might be saying, okay, this is not this particular thing is not this graph, right? Now we're going to add stuff into it. Now we have reached a state where we're taking an input, an initial state, going into LLM, and that LLM is generating a tool call. Now let's build on top of that. Now, all right, but if you see, if I resort to something, some kind of query that does not require a tool call, it will work just fine. So if I say, hi, how are you, and if I check the response, you'll see content, hello, I'm here and ready to assist you. So it gave a response, right? It can generate a tool call, it can generate a generic LLM response. Okay, now let's build on top of that. This particular thing which we are designing right now can be termed as a router, because it is routing between two different paths. That's why I've written router over here as heading, and we are creating it again. Let's rebuild this. We know the idea, let's build on top of that. Okay, now you see I have imported these two modules. One is a pre-built node called as tool node, and one is a pre-built conditional edge called as tools condition. We'll see how to use them. We define the state again. We need not define this again, but I'm defining it again to avoid confusion. And then we define the node function for the LLM, same as the earlier one. Tool calling LLM takes an input the messages state and then returns ln.invoke. Cool. Now instantiating the builder object, then add node, the tool calling LLM. We basically added this node, and then I added another node, which is the tools node. Now what is this tools node? This is the node that will take an input, the tool call, and will return the output of that particular tool, in this case the multiplication tool. So let me add another. Okay, the tool node here will take in input, the tool call, and provide the output as per the multiplier tool, because that is the only tool that we have in this particular picture. Now, how to add this tool? For this we use the tool node from LangGraph. So the syntax is, if I want to use tool node, let's just know about this. So it is basically a node that runs the tools called in the last AI message. Cool. So we add node, the name of the node is tools, and we define it as a tool node. So what it will do is, it will take in input the last AI message, which should be a tool call in this case, and it will run this particular node. So the syntax is builder.add node. Here we can have the node name again, node name, and then if we want to define it as a tool node, just go here and write tool node, and inside this we need to have the tools list, the list of the tools that we are trying to call. So here the tools list was tools already, so this created a tool node for us. Now we have this LLM node and we have this tool node. And now we add the edge start to tool calling LLM, start to tool calling LLM. Now we have to add this and add conditional edge. One way would be to create a custom function for this conditional edge like we did before, but here we can use the pre-built conditional edge called the tools condition. Let's see what it does. So it is using the conditional edge to route to the tool node if the last message has tool calls, otherwise it will route to the end. So what it's doing is, if the LLM's response contains a tool call, then this conditional edge will choose this particular path that leads to the tool node. And if the LLM's response does not contain a tool call, that is, it's basically a generic LLM response, then it will route towards the final stage. I should not use it as blocks, maybe. I should just make it better in this way. um, directly over here, and I can add no tool call. Okay, and I will mark this as blue. All right, and I will also delete this, and this will make it better for understanding that there is only one node. So simple as that. If the LLM's response contains a tool call section, it will call the tool. If it does not contain the tool call, it will straight up go to the end. Okay, how to define it? Very simple. The conditional edge name, and just use tools condition here. What it will do is it will take in input the latest AI message, and if it has used in the conditional message, route to the tool node is the last message, that is the message from the last node, which here is the LLM node. If it has a tools call, it will go to the tool node, which we already defined, or else it will route to the end. Okay, now we add this particular edge, tool to final state or tool to end. Got it. Cool. Now let's compile this particular graph. We compiled it, and now we visualize it. There is a start going to tool calling LLM. Now based on a conditional edge, it might call tools, it might go to the end. If it contains tool call section, then it will call the tools, and if not, it will go to the end. Cool. Now let's try to execute this. I'm defining this particular message as this. Okay, let me write it again for better understanding. Initial state equals messages. Now the message should be a user query, so it's good practice to provide it in this way, the human message object form. Content equals, now my content will be, let's try something that will initiate a tool call. Okay, just multiply 2 and 3 again. Okay. This is the initial state, and then go for response equals graph dot invoke, and we can go for this initial state. Okay, let's see how the response looks like. Response, yeah, we got it. All right, maybe I was running the older graph that I created on the top, and now we are getting the answer. All right, so it's important to learn actually what things can go wrong while you are executing it. All right, so we got this particular response. Now we will try to see it in a better way. For R in response, just go to every single thing will be R in response. Is it true? No, I think we should go for R in response messages R dot pretty print. Yes, sir. Now you see, the human message was multiply 2 and 3, and then the AI message was a tool call that provided the arguments, and then the tool message was 6. So the final answer, or the final state, is this 6. And if we asked it a generic question that did not require a tool call, let's see what happens then. Took the human message, got the AI message. This AI message did not have any tool calls, so it just went to the end, and this is the end state. Cool, this is actually working. So we have figured out how to go about the router agent. Now, one interesting thing I'll show you here. one scope of improvement that will lead us to explore the next agentic workflow. Today, say that if I asked it to do something like multiply 2 and 3 or multiply 2 and 5, the response which I will get is 10. Only 10. Is that how you want to respond to the user if it's asking something like that? And is it suitable for cases where we might have multiple tools? What I'm saying is, in this particular router agent, wouldn't it be good if we respond with something like multiplying 2 and 5 gives us 10, so that it looks like a proper LLM response and not just 10 as if we ran a function in the backend. Everyone knows we ran a function actually. So what we can do is we can supply this particular result that we got from the tool back to the LLM so that it can decide what to do next. What I mean is, say that we have multiple tools. We follow the same workflow, we get a response from our tool, and we feed it back to the LLM, and the LLM looks at that result, digests it, and then makes a decision whether to push this as an output to the user in a pretty format, obviously in a natural language format, or this is not good enough, I need to call another tool. What that will do is, that will create or that will add a very good dynamism into our workflow, a feedback loop that ensures that all the tools that we have provided to the LLM gets used efficiently, and the response that we get from the LLM, from the workflow, from the graph is actually a good one. How to do it? Let's see. This particular workflow or this particular graph which I was talking about is called a React agent. Now, what are the three basic features of this React agent? First is act. It lets the LLM decide which tool to call, which means that basically works good with, or it is more suited in conditions where we have multiple tools. Production ready applications, we will obviously have multiple tools. Second is observe. What we are trying to create is a feedback loop where the output of the tool is being observed by the LLM so that it can make a decision. Third is reason. The LLM reasons on that particular output and then makes a decision. Let's look at this particular flow. Again, it starts off with an initial stage, goes to the LLM, then the tools condition that checks if it has a tool call or not. If it has a tool call is generated. Again, I should probably make it a bit better understandable. Tool call, make it red. Yes, sir. And do the same here. Pardon me for this thing, I'm trying to improve it on the fly. Alright, tuck, no tool call, should be blue. Alright, initial state, LLM, take it to the tools condition. If it has a tool call, go to the tool. If it does not have a tool call, straight up go to the final state or go to the end. But if it has a tool call, take it to the tool execute it, get an output, and then feed it back to the LLM, and the LLM decides whether to again follow this path and call a tool, or this time straight up go to the final state. We actually do not need this part, just realized. Alright, so this cycle continues until and unless the LLM decides that okay, I have used all the tools in my arsenal to get the optimal response and I need to provide the output. Cool. Let's see this in action. Okay. So first of all, we are defining the tools. We have a multiply tool, we have an addition tool, we have a divide tool. I'm calling it the multiplier tool, the adder tool, and the divider tool. Adding all of my tools into the tools list and then binding them to the LLM. Cool, this is pretty understandable, this section. Then what I'm doing is, to my messages state, I'm trying to add a system message. System message is something that guides the LLM on what kind of role it has to play. System message is simply you're a helpful assistant tasked with performing arithmetic on a set of inputs. Yeah, on a set of inputs. And then we define the first node function, that is the assistant, the LLM. This we are calling the assistant. State messages state as input and response is simply invoke. Now you see we have added the system message to the state to generate the response, and then return messages response. Cool. Now from LangGraph we import the start, state graph, tools condition, tool node, create the builder object, adding nodes. We added this assistant or the LLM node. Let me just write assistant over here because that's what we are calling it. And then we are adding this conditional edge, goes from assistant to the tools condition. This just checks whether the assistant's response is a tool call or not. If it has a tool call, it takes it to the tool to generate an output. If it does not have a tool call, take it to the final state or to the end. Then we add an edge from tools to assistant. Now this is the feedback edge. Feedback edge. What it's doing is it's connecting the tools node back to the assistant node. Oh, by the way, we also created the tools node over here. My bad. You know how to connect this, similar to what we did before. Now we are at the feedback edge. Now we compile this builder object and we visualize it. Alright, see. We start, go to the assistant LLM. It might go to tools, it might go to end, but if it goes to tools, there is a feedback loop and the tools output again goes to the assistant. This feedback thing might go on till the assistant is satisfied that okay, it has used all the tools in its arsenal to generate the optimal output, and it goes to the end for the final response. Let's check how it works. Now, because we have a multiplier tool, we have an additional tool, adder tool, and we have a divider tool, so we can go for some complicated query like this one. Multiply 2 and 3 and then add 10 to it and then divide it by 2. This is the input, or I can call it the initial state. Okay. Now I can go for response, invoke input. Instead of input, it will be initial state. I'm just making things uniform for you to understand better. And now I can go for r in response dot or messages r dot pretty print. Now see, took in the human message, multiply 2 and 3, and then add 10 to it, and then divided by 2. The answer that we get should be 8. Okay. Went to the AI message, called the tool, the multiply tool and the add tool. The multiply tool with 2 and 3 as arguments, fine. The add tool with 6 and 10 as arguments. So 2 into 3 is 6, and then 6 and 10. Cool. Got two results, 16 and 6. Again fed that back to the assistant or the LLM, and again it went for a tool call. Now it went for the divide tool call. Argument 16 and 2. Now it got the answer 8. Now it again went to the AI message, I mean the LLM, and this time, after going through this loop twice, now the assistant is satisfied that okay, we have the right response now, and it went through this path without generating a tool call. It did not need any tool right now. It just generated a good response. What I mean by a good response is, instead of responding just by 8, it responded by the result of multiplying 2 and 3, adding 10 to it, and then dividing by 2 is 8. Proper, right? So this is about it. This is about the React agent. And yeah, now in the next sessions, guys, we'll be focusing more into more complicated graphs. We will be looking into more features that LangGraph has to offer, like memory, human in the feedback loop, and stuff like that. And we can just go deeper into the LangGraph universe and the Agentic Workflows universe. Thanks. Bye-bye.